Today's class we will see about energy stored in a capacitor. You take down this derivation, derive the expression for the energy stored in a parallel plate capacitor with the air between the plates. How does the stored energy change? How does the stored energy change if the air is replaced by a medium of dielectric constant K? Dielectric constant K. So we will derive the equation for energy stored in a capacitor through this derivation. The question is, derive the expression for the energy stored in a parallel plate capacitor with the air between the plates. How does the stored energy change if the air is replaced by a medium of dielectric constant K? Now I'll write here a solution. Let us consider a parallel plate capacitor which is charged by a battery of V volts. Let C is the capacitance of the parallel plate capacitor and V is the battery voltage. Now we need to find out what is the energy stored in this capacitor. Let us say C is the capacitance of the capacitor and it is charged by a battery with battery voltage V volts. So let Q is the charge and V is the potential difference across a capacitor at any instant during its charging. Let Q is the charge and V is the potential difference across the capacitor at any instant during its charging. So we have assumed small q is the charge and V is the potential difference across the capacitor at any instant during its charging. Now the small work done in storing an additional small amount of charge dq will be given by, so small q is the charge at any instant. Now is the charge increased by a small amount dq, what is the work done in increasing in storing this charge? So the work done small work done in storing an additional small charge dq against the repulsion of charge q already stored in it is given by small work done in storing an additional small charge dq is given by dw is equal to v into dq. And we know that we have assumed that q is the charge and v is the potential difference across the capacitor instead of charging. So we can write this q is equal to cv. So here we can write q is equal to cv or v equal to q by c. So we can substitute that here. dw is equal to v, that is q by c, into dq. Now if the capacitor gets charged to a total charge of capital Q, the total amount of work done in storing the maximum charge Q on the capacitor will be given by, therefore the total amount of work done in storing the maximum charge Q on capacitor is W is equal to, so we can get this by integration or summation of work done in storing small amount of charges, 0 to the total charge is capital Q we took, into Q divided by C into dq. Integrate this. 1 by c is constant, so we can take it out. 1 by c and integration of q with respect to dq, so it is q square by 2, and put the limits from 0 to capital Q. So this we will get half C into capital Q square. So W is equal to half Q square by 2, half Q square by C. W is equal to half into Q square by C. This is one equation. We can get the energy stored in the capacitor in other form also. So this energy gets stored in the form of electrostatic energy. So energy stored in the capacitor we can write finally as, now we can substitute Q as CV. Q is CV whole square. Q is equal to CV whole square divided by C. So this will give us another equation for energy stored as half CV square. Also we can substitute V is equal to Q by C or we can substitute C is equal to, from here, C is equal to Q by V. We have C is equal to Q by V. So that will give us another equation, half into C is Q by V. Q divided by V into V square. 1V and V will get cancelled. So this is also equal to half QV. This is another equation. Half QV is another equation for the energy stored in capacitor. We can use any of this equation. So finally we will write all these equations together. We'll write the work done gets stored in the capacitor in the form of electrostatic energy. So the energy stored in capacitor is we'll write it in different forms. U is equal to half Q square by C or it is also equal to half CV square or it is also equal to half QV. There is another question here. If you introduce a dielectric, what happens? And we know when we introduce the dielectric, in case of, if the capacitor is connected to the same voltage source V, the battery voltage will remain the same and the energy stored will become K times the energy stored when it was air was the dielectric, because I'll write here by introduction of dielectric medium with dielectric constant K, the value of mu C is equal to K in the value of capacitance becomes Kc. By introduction of dielectric medium with the dielectric constant AK, the value of capacitance becomes Kc. Therefore, energy stored U is equal to, we have half CV square, so it is half K into CV square. because the capacitance value now changes, and the capacitance, if it is connected to the battery, its voltage will remain the same. So it becomes K times C into V square. By introduction of dielectric medium, the energy stored becomes K times the energy stored when the medium was air. So KCV square.